basically I'm using the supersonic expansion of gas through a Laval nozzle, which is one of these, to cool my gaseous reagents down to temperatures as low as about 60 Kelvin. So to measure the rate coefficients, I'm using lasers. So I'm using pulse laser photolysis, laser-induced fluorescence of a radical, which is the hydroxyl radical. So we need lasers in this case to measure the temporal evolution of the OH radical, to look at how it decays away, and therefore to look at the rate coefficient for the reaction which I'm looking at. So I've got two lasers here. This is a YAG, which pumps our dye laser, and this is our probe laser, which excites the hydroxyl radical to a higher state, then it emits fluorescence, which we collect using a PMT. So we use this laser because it's tunable, and we can get all sorts of wavelengths, so we can look at different radical species using this. So this is delivered to the chamber using some turning mirrors, and it's enclosed in this pipework, so it's fully enclosed and safe, so we don't get any light scattered anywhere. The second laser that we have here, which is for the photolysis part, is the eczema laser, which is just here. And this is quite a high power UV laser which photolyzes our OH precursor, which in this reaction is tertiary butyl hydroperoxide. So we change the time delay between these two lasers, and then by changing the time delay we're looking at how quickly the OH decays over time after it's produced. So this is delivered to the chamber by some turning mirrors, and it goes along the chamber, along the axis of the chamber, and the dye laser crosses it perpendicular in the centre of the chamber. So this laser area where the two lasers come in is fully enclosed by some black sheeting, which I designed so no laser light can be reflected or scattered outside of the area. We've also got some thick black laser curtains, which ensures that if we're aligning, which I am doing at the moment, that no light can bounce off anywhere. So the alignment process, we use bits of paper to see where the laser's positioned as you look down the chamber. We also have alignment tools such as this black tube and some circular bits of paper with holes in, which guide us towards the centre of the chamber. So we've got also a small Heaney laser here, which we align initially down the centre of the chamber, and then we use this to align both the other lasers too. So we've got a YAG pumped dye here, and because of space constraints we've got a periscope system which delivers the light from the YAG up into the dye laser. So we've got a tube here which prevents any light from being refracted or anything outside of this area. And then we've got two mirrors which turn it up into the dye laser. This is called periscope arrangement, and because if you opened this lid it could potentially go into the eye. It can be quite dangerous, but we've got some orange shielding here which prevents any light escaping, and we also usually have on this sign just reminding people to be careful when using the periscope arrangement. So the reason that we're using a YAG pump dye and not just the YAG itself is because we need to make light which is resonant with our hydroxyl excitation. So we're using the YAG to provide initial light to the dye laser, which then excites dye, which is just positioned in these bottles, which is circulated around the laser, and that emits light at a wavelength which we then frequency double to produce 282 nanometer light, which is then delivered to the chamber, and that excites the OH transition. So the dye that we're using in this case is rhodamine G, which is in a methanol mixture, and that's circulated around through these tubes through the dye laser itself. But the reason that a dye laser is quite good is you can easily change the dye and probe a number of radical species, so it's quite a flexible laser. So if we take a look inside, you can see that there's two cuvettes of the dye, which is here and here, and that's where the initial YAG light excites the dye and then that produces the required wavelength of light that we're after. And then at this stage here, just before it goes into the turning mirror, it goes through a frequency doubling crystal, which then turns the light to 282 nanometers, and that's the light that we use to probe the OH radical.
Rebecca, you insisted that we wear these safety specs before you lifted the covers on the dye laser. Why is that?
So it's always important to wear safety glasses in a laser lab. The laser light which is produced after the frequency doubling stage is UV, and these perspex safety glasses can help cut out most of that, which reduces the risk. When you're aligning it, ideally you want to wear specialist safety glasses, but this is fine, and it cuts out a lot of the dangerous light which can damage your eyes.
Right, okay. And I guess the camera guys wore them in case of scatter.